Chapter 6 is about oral medication dosages, and this really is the beginning of the realistic calculations that you do in this course. Here we're going to turn prescriptions into tablets, capsules, or milliliters if it's a liquid medication. And some of these calculations will factor in the patient's body weight or even their body surface area. Surface area would be literally the skin area covering the body. So let's start off. Their units are what drives all these calculations, just like everything else in this course. And let's start off with a real simple example. Here's our first example. The order is for 250 milligrams. The drug comes in 125 milligram tablets. How many tablets will the patient receive? In working these problems, you're going to see me get into some pretty consistent habits. When there's patient information, which can be body weight or body surface area, then I list that first in my calculations. And then whether that's there or not, what would come next would be the prescribed dose. Now, it's not necessarily the dose you're going to give the patient that we have to calculate, but the prescribed dose here is 250 milligrams. So I'll begin with that, 250 milligrams, and I'll put that over 1. Students seem to be a little more comfortable multiplying fractions when you have we list them as a fraction over 1, and that's perfectly fine. Now, the drug comes in 125 milligram tablets. This is a drug concentration. A drug concentration is the amount of drug that's contained in a particular unit. In this case, our unit is tablets. So the drug concentration comes next after the prescribed dose, and notice that we have 125 milligrams equals to 1 tablet, and we normally abbreviate tablet, TAB. This is actually a conversion, similar to 60 milligrams equals 1 grain, or 1,000 milligrams equals 1 gram. It's a conversion, but it's given to you in relation to this particular drug. So what I do is I form a fraction out of this, and I want to cancel milligrams. So milligrams needs to go in the denominator, and tablet, 1 tablet, goes in the numerator. So another way of looking at this is that we're replacing milligrams with tablets. So tablets need to be in the numerator. Alright, so these units canceled, and my units left over are tablets, which is what we're looking for. So this comes out to be 250 over 125 tablets, and that's an easy one. That's 2 tablets. So there's what we'll give the patient. So again, very fundamental type of problem. We begin with the dosage that's ordered, prescribed, and then we do a conversion into the form in which the patient will take the drug. This next example is a little more complicated. The doctor prescribes 0.018 grams. The drug is available in 6 milligram capsules. Now, how many capsules will the patient receive? Alright, well, what's going to make it a little more complicated is that the order is in grams, but the capsules are in milligrams. So this is going to lead to an extra calculation, extra conversion. Alright, so the prescription is 0.018 grams, and the capsules are measured in milligrams, so we're going to need to convert grams to milligrams. So we have 1,000 milligrams over 1 gram, and that allows us to cancel the grams units. So now we're out to milligram units, and then 1 capsule is 6 milligrams. So where do I put capsule? Well, we want to end up with capsules. That's the numerator. So capsule goes on top, 1 cap, over 6 milligrams. Of course, the other important thing about this is that milligrams must cancel. So the units cancel, leaving capsules, And we have this calculation, 0.018 times 1,000 over 6, and that's capsules. Here I think it would be easy to multiply 1,000 times this decimal number, and multiplying by 1,000 means we're going to, make this number larger by 3 places. So I count over 3 places, that becomes an 18. So this is 18 over 6, which is 3 capsules. So there we go. This next example is an example of a liquid drug calculation. And although most of the problems you're going to work are in the metric system, I'm going to throw some apothecary and household stuff at you once in a while just to keep you on your toes. The order calls for 1 1/3 grains of a drug. The label reads 5 milliliters equals 200 milligrams. How many teaspoons will you administer? Alright, well, this is the drug concentration right here. Because the drug comes in a liquid form, it's in a bottle, and 5 milliliters of liquid will contain 200 milligrams. So let's start off with the dosage, which is 1 1/3 grains. So I have 1 1/3 grains. And let's write this in a more friendly, calculatable form here. 1 1/3 is 4/3. 1 times 3 plus 1 is 4. So it's 4 grains over 3. And let's see, the concentration is in terms of milligrams, not in terms of grains. Remember, milligrams is the weight unit here, and grains is a weight unit. So we need to convert grains to milligrams. So what is that? 60 milligrams is 1 grain. So that takes care of grains. And now we can use the drug concentration, which is 5 milliliters over 200 milligrams. Again, don't be careless about where you write these. Some problems you may have milligrams over milliliters. Just all depends. But here we need to cancel milligrams and replace it with milliliters, and that's why milliliters goes on top. All right, and then we get down to teaspoons. Well, 1 teaspoon is what? 4 milliliters, or is 5 milliliters. I think I'm just going to calculate this out and see what we have, and we'll estimate from there. So this is 4 times 60 times 5 over 3 times 200. And it looks like we can do some nice canceling here. For example, the 3 cancels 60, leaving 20. And then 20 cancels 200, leaving 10. And so we have 4 times 5 over 10. Well, that's 20 over 10, which is 2 milliliters. All right, so how many teaspoons? Well, that's about half a teaspoon, isn't it? 2 milliliters times 1 teaspoon per 4 milliliters would give you, milliliters cancel. So that gives us 2/4 or 1/2 teaspoon. All right. I waited toward the end to do this because the other conversion is 1 teaspoon is 5 milliliters. And so I wanted to say that toward the end because I have a choice on teaspoons, 4 milliliters or 5 milliliters. I want to pick one that's convenient. And if I had a 5 here, then this would be 2/5 of a teaspoon, a little bit under a half. So we'll call it half a teaspoon. When one of my daughters was young, she came under some medications for a persistent problem, which lasted a few years. Unfortunately, she outgrew it. But when she was rather small, the first dosage of this particular medicine was 1/4 of a tablet. So we had to go out and get a little pill cutter and cut these little things. They were tiny little tablets, cut them into 1/4 pieces. as she got older, it went from 1/4 to 1/2, and then to 3/4, and 3/4 was particularly a problem. And then eventually she went up to a full tablet, and then outgrew it. But some tablets come in scored form. A scored tablet has a groove cut in it for convenience of cutting, and so the groove makes it much easier to slice it into half. I don't know if there are tablets which have more than one groove, which will allow you to cut them into more than two pieces. Don't know if those are out there, but they may be. In any event, your textbook's latest edition, for some reason, leaves out any discussion of scored tablets. They used to talk about it, and I don't know if this was an oversight or what, but there's still some problems in the textbook, which use scored tablets. And I just think it's important that you learn about them. So here's an example of one. Prescribed dose is 300 milligrams. The drug comes in 120 milligrams scored tablets. How many tablets will the patient receive? All right, so this really works the same as any other problem. I'm going to start with the dosage, 300 milligrams. And the concentration is 1 tablet is equal to 120 milligrams. So as usual, milligrams cancel, leaving tablets. And we end up with 300 over 120. So that reduces to 30 over 12. And let's see, if I continue to reduce, this will be 10 over 4, 5 over 2, or 2 1/2 tablets. So ordinarily you would round up to 3 tablets, and but being a scored tablet, you have the option of giving a 1/2 tablet also. So in this case, 2 1/2 would be acceptable for a scored tablet. If it doesn't say scored tablets, then all you can give are a whole number of tablets. Unless there's a particular concern there, I suppose you could talk to the doctor and clarify about this. But that's beyond my ability to advise you on. So in any event, the scored tablet can come in a half a tablet quantity, but it also can come into in full quantities, whole numbers as well. Over-the-counter drugs tend to come in one-size-fits-all categories, especially for adults. But there are a lot of drugs which must be fine-tuned to a person's body weight, so that a larger person get a larger amount, for example. I suspect you may see even more of this with pediatric dosages, since there's such a wide difference between sizes between infants and older children. So if you're lucky, you won't have to convert from pounds to kilograms, because many scales these days carry both systems on it. So they'll measure weight in both pounds or kilograms. But you still need to learn it for this course. And it turns out, since almost all drugs are measured in terms of the metric system, then it turns out the conversion will always tend to go from pounds to kilograms. And so what this amounts to, because there are two choices, amounts to either multiplying by 0.45 or dividing by 2.2. So let me illustrate that. Call it, there are two choices here. 1 kilogram is equal to 2.2 pounds, but also 0.45 kilograms equals to 1 pound. So I tend to use the 2.2 pounds myself, and it's my personal preference. Most cases I'd rather divide by 2.2 than multiply by 0.45. But it's up to you which one you use. The thing to remember is that these are not exactly equal to one another. So the answer you get, for example, if you use this conversion, I use that conversion, our answer is going to be off by a little bit. Not much, but off by a tiny bit. Okay, so to give you an example, suppose a patient weighs 138 pounds. Then convert this to the metric system, I need to cancel pounds and replace it with kilograms. So my preference is 1 kilogram divided by 2.2 pounds. All right, so in this calculation, pounds cancel, and we get 138 over 2.2. And I'm going to get rid of the decimal, at least temporarily, by lining up the decimal points and then sliding the decimal points over. So this becomes 1380 over 22, and that reduces to, what is that, 690 over 11. All right, now I can divide by 11 pretty well. I can usually do it in my head. And let's see, so that would be 62 point, what was that, 32, 11 would be 62.7 kilograms. But let me verify that with long division. So I'm going to divide 11 into 690. I don't recommend you do those kinds of divisions in your head, but I have some confidence because I've been doing this since the pre-calculator era. So it goes 6 times 11 is 66, subtract, we get 30. And now it goes a 2, 22, leaving an 8. Decimal point. Next one is going to be 7. And then we're going to have a 2 next of all. It turns out when you divide by 11, you get numbers which repeat every 2 places. So this is going to go 72, 72, 72, 72. And but anyway, in any event, this would round off to, if we went to 1 decimal point, this would be 62.7 kilograms. All right, so there's that conversion, dividing by 2.2 pounds. The other way to convert, let's see what we get. And so it'd be 138 pounds times 0.45 kilograms over 1 pound. So pounds again cancel, and I have to multiply 0.45 times 138. So let's see, I'll do that over here. 38.45. Let's see, 15, 19. There's 690. And then, you see 32, 12, 15, 4, 5, 0, 11, 1, 7, 12, 1, 6, 62.1. 62.1 kilograms. So like I said, they're going to come out very, very close. In fact, if you round it off to a whole number here, in one case you'll get 63 kilograms, here you get 62 kilograms. 1 kilogram at this weight level is not going to make a difference. But you should always, of course, strive for accuracy. But who's to say what's accurate here? Actually, the exact conversion is neither of these. And so I think it's more like 2.205, but I haven't worked it out lately. So in any event, there are your choices. I don't care which one you use. Some people are much happier by multiplying than by dividing. If I was converting 200 pounds to kilograms, then I think I would choose the other method. 0.45 kilograms per 1 pound. Their multiplication would be very, very simple. It would come out to be 90 kilograms, wouldn't it? So there may be some situations where you'd want to switch off. And if a person weighed 88 pounds, 88 divided by 22 is easy. And so 88 pounds would work out to exactly 40 kilograms. So it's nice to know them both and be flexible enough to use them both to your advantage there. In this example, a patient weighs 40 kilograms. The order calls for 200 micrograms per kilogram. The drug comes in 4 milligram tablets. How much will the patient receive? So the patient weighs 40 kilograms. I like to begin with the patient information. And so we'll put her weight down, 40 kilograms, and that just comes by itself. So I'm going to write it as a fraction, 40 kilograms over 1. So we took care of the patient information. Now the prescription is 200 micrograms per kilogram. So this is a unit of its own. It's a fraction because the little word per is a Latin word which means to divide. And so 200 micrograms per kilogram is 200 micrograms over kilograms. So here's a compound unit in which we have actually 2 units to go with it. It's sort of like if you get paid by the hour, you get so many dollars per hour, or maybe your car gets so many miles per gallon. Those are compound units. All right, so now I'm going to write it just as I see it over here because I want to cancel kilograms off and replace it with the weight of the drug, not the weight of the patient, but the weight of the drug. So we'll have 200 micrograms per kilogram, and this cancels the kilogram units. The concentration is 1 tablet is 4 milligrams, so we need to convert to milligrams. So we have 1 milligram is 1,000 micrograms. So that cancels off micrograms. And now we can bring in the drug concentration. 1 tablet is 4 milligrams, so I need to cancel milligrams. 1 tablet over 4 milligrams. There we go. So notice how all the units cancel off nicely, and we're left with tablets as a numerator. All right, so let's recopy this and we'll do some simplifying. So 40 times 200 over 1,000 times 4. And we could cancel, or we could just multiply across. Actually, well, let's cancel. I can cancel off 2 zeros here and another 0 there. And then the 4 cancels. And we're left with 2. So equals to 2 tablets. The order calls for 2 milligrams per kilogram. The patient weighs 213 pounds. And the drug comes in 50 milligram tablets. How many tablets will the patient receive? All right, so this time we're going to need to convert from pounds to kilograms since the prescription is given in terms of kilograms. Actually, it's milligrams per kilogram. So, as usual, let's begin with the direct patient information, which is his weight, 213 pounds. And we're going to need to cancel pounds and replace them with kilograms. So I'm going to use 2.2, my preference. And so I've got 1 kilogram is 2.2 pounds. And that cancels pounds, replaces them with kilograms. So here I'm dividing by 2.2. As I said, much of the time these end up being divisions by 11, which is not too bad. It's perfectly fine if you want to multiply it by 0.45 kilograms per 1 pound. But then you have a 2-digit number multiplying a 3-digit number, which can be a little more complicated. All right, so what's next? We have the prescription, 2 milligrams per kilogram. So that's going to cancel the weight in kilograms and replace it with the weight of the drug. So we cancel kilograms, and now we're at milligram units. And finally, the drug concentration is milligram tablets. So 1 tablet equals 50 milligrams. I need tablets in the numerator. 1 tablet over 50 milligrams. And milligrams cancel, leaving tablets. So our calculation is worked out as far as the units go, and now it's just a matter of finishing up the arithmetic. So let's rewrite that kind of neatly here so we can see what we're looking at. 213 times 2 over 2.2 times 50. And this is going to be tablets. Now we could do a little simplification. We could, for example, cancel the 2 with the 2.2, leaving 1.1. But then we're going to have to divide by 50 also. Or we can multiply 50 times 1.1 and get 55. Divide by 55. So, there's a number of ways to do these problems. What I'm looking at is 50 times 2.2 is 110. And so dividing by 110 is almost like dividing by 11. So that's going to be my choice. And on top, let's multiply 2 times 213. That would be, what, 426 over 50 times 2.2 is 110. So there's my problem. I'm dividing 110 into 426. And I'm going to make some room up top here. So I'm going to erase the problem to make room for the long division. So dividing 110 into 426. And let's go ahead and put the decimal point in. So 110 goes into 426 3 times. And this will give us 330. Subtract would be, what, 96. Bring another 0 in. And let's see, 110 goes into 960 8 times. And so that would be 880. And, well, that's enough, is what we need, because tablets come in wholes. And so, actually, I believe this is 3.87 tablets, as it works out to, looks like to me. But in any event, it's going to round up to 4 tablets. So it's very close. So let's call it 4 tablets. There are some medications which are calculated based upon a person's body surface area. So the body surface area literally is the amount of skin covering, how much skin we have. And there's no simple way to directly calculate that on a person, but there are some very good estimates which can be obtained by using the person's height and their weight. And now these calculations involve square roots, and they're rather messy. There's the formulas given in your textbook, and these formulas were worked out about 90 years ago, in fact, and they're quite good. But I'm not going to expect you to use the formula with the square root in it, and imagine trying to calculate that without a calculator. So we're going to use a chart called a nomogram. But let me just talk a minute about, because this is an area of interest for me. I like, when I teach algebras, sometimes I like to talk about how proportions vary in our world. And we think about mammals. We mammals, humans, dogs, cats, horses, pigs, elephants. Mammals, by nature, maintain a constant body temperature. And so we have an internal thermostat, and our metabolism is partially built around maintaining that constant body temperature. Birds are also warm-blooded animals and have a similar mechanism for maintaining body heat. Reptiles are not. They're cold-blooded, and they have no body temperature to maintain. So reptiles tend to sort of shut down when it gets cold. But mammals heat up. Now, where does that heat go? All right, so your body is burning energy, takes in food, burns off energy, and creates this heat in the process of doing everything else. The heat radiates through the skin. And so it would seem like the more skin you have, the more heat you would radiate out. And if you have less skin, you would retain heat. Well, it turns out it's quite interesting, because if you compare a small animal to a larger animal, or a small human to a larger human, the larger animal or the larger human actually has less skin per body weight, because as we grow in size, our volume grows according to 3 dimensions. But yet and volume is what's determining our body weight. But the skin area grows according to 2 dimensions, length times width. And so it turns out that if you had a person who was actually twice as tall as another person and they had the same exact shape, then the person twice as tall would weigh 8 times as much, 2 times 2 times 2, 8 times as much, but would have only 4 times as much skin area, 2 times 2, but be twice as tall. And so when you think about those dimensions, it gives you some insights. And so actually the skin on larger animals is considerably less in relation to the amount of body weight. And the body weight is what determines the heat production. So that's why big elephants have almost no fur. If you look at an elephant, you'll see a hair sticking out here, and maybe another one over here. Almost no fur at all. It's because elephants have a heat problem. It's very easy for them to overheat. Their ears are not for sound collection, they're for radiating heat. The big elephant ears are literally like a car radiator. A lot of blood goes through them, and that cools off in the air. And elephants like mud puddles. If you go to, and what do they eat? They eat grasses and leaves, very low energy food, because they don't, if they ate a lot of high energy food, they would produce too much heat. And that would be a problem. If you look at the other extreme end of the spectrum, little rodents, rodents like mice and rats and gerbils and shrews. In fact, the smallest mammal is a particular species of shrew is smaller than a mouse. That little guy has to eat 3 times its own body weight every day. Imagine eating 3 times your body weight. Wow. And but if it doesn't, it's going to die, because it is so small. It has far too much skin per body weight, and so that skin radiates all the heat away very quickly. And so rodents, small mammals, have to eat a lot, and they eat high energy food like grains and insects to keep that engine running, to keep that heat production up, because the heat dissipates too quickly. Okay, well, if you think about human beings, the larger people tend to feel a little warmer, and but I think things tend to even out after a while, because the body adjusts. There are different metabolic rates, and I don't understand all that stuff very well. But I have known people who've undergone both either a rapid weight gain or rapid weight loss. And those who have gained weight, a lot of weight in a short time, tend to be very warm. And it's because they're producing more heat than they're accustomed to losing through their skin. And people who lose weight, a lot of weight in a hurry, tend to be rather cold. You'll see them wearing sweaters in the middle of summer. I've known people like this, and that's because they suddenly find themselves with more skin area per body weight, and so they're losing heat a little more rapidly. So anyway, those are some, I think, some interesting considerations, mathematical considerations. This is part of mathematical biology in terms of thinking about how dimensional analysis affects the way animals are built and their physiology. And so somehow this enters into medicine. I'm not sure quite how. Your book mentions that there are some cancer drugs. A lot of cancer drugs tend to be based on body surface area. And easily you can imagine a drug which has some kind of skin sensitivity would also be, that prescription would be based upon body surface area. So let's do an example. I started with a simple example to introduce body surface area. The order calls for 5 milliliters per meters squared. This is square meters. The patient's BSA, that means body surface area, is 1.2 square meters. How many milliliters will the patient receive? Well, this is a liquid drug, obviously, because we want milliliters. Now, body surface area is measured in terms of square meters. And a meter is 39.37 inches. So it's a little bit over 3 feet. And a square meter would be, now this board is 3 feet by 4 feet, so this is approximately a meter from top to bottom. So most of this board would be 1 square meter. So that means this patient has 1.2 of those covering her body, or his body. And so that would be approximately the amount of skin equal to, say, the size of this board. Pretty close. All right, so now in square meters, algebraically, when you multiply a letter times itself, you get a second power. And so meters times meters gives you square meters, or meters to the second power. So we normally abbreviate it m to the second power, just like in algebra. All right, so the patient's information comes first, 1.2 square meters. And the prescription is 5 milliliters per square meter. So we want to cancel square meters and replace it with milliliters. So this gives us 5 milliliters over 1 square meter. So that cancels the square meters. And 1.2 times 5 is 6 milliliters. So that's the calculation. It's really no different than about anything else we've done here. Square meters is just another type of unit which can get canceled. Your textbook provides a handy chart for calculating body surface area called a nomogram. And even though your textbook says it's been reprinted with permission from another source, actually that exact chart first appeared in 1916 in a medical journal. And all this can be found online. You can find other kinds of nomogram charts there too. In fact, a nomogram is a general term for a chart which uses at least 3 scales. And these 3 scales, the way you use it, you connect points on 2 of the scales with a line, and then the reading on the 3rd scale is the one you're looking for. So that's sort of a general definition of a nomogram. And there are nomograms in other areas of medicine for other kinds of purposes. But this one has height as the left-hand scale, and it has body surface area as the middle scale, and then the right-hand scale is weight. So if you look in your textbook, you'll notice that the height is given in both inches and centimeters, and weight is given in both kilograms and pounds. The body surface area is given in terms of square meters. So it's rather nice because you don't even have to convert from pounds to kilograms or from inches to centimeters. Here you can just look them up both on those charts. Very handy. So it's very simple to use. To give you an example, suppose a person is 177 centimeters tall. So that comes out, we'll say over here, 1.77 centimeters. And that's around 5'10", it turns out. It's 1.77 meters, but there are 100 centimeters in a meter, so it would be, and I wrote 1.77, I meant 177 centimeters. All right, and anyway, the weight is 81 kilograms. So suppose that's over here, 81 kilograms. All right, so if you had that information, then you would connect the points with a straight line. And you should try this in your book, see if you get the answer I get. This came out to be, I get 2.05 square meters is the number on that scale that crosses. So you could use a straight edge, edge of a piece of paper, index card, just to connect these scales, and then based upon height and weight, and then the middle number is the proper body surface area. So let's do a problem with that. Here's our full example using body surface area. The order is 30 milligrams per square meter. So there's your giveaway, it's body surface area. The patient is 5 feet 7 inches tall and weighs 163 pounds. The drug label reads 1 milliliter equals 16 milligrams. In other words, 1 milliliter contains 16 milligrams. How much will the patient receive? All right, well, we have to go to the nomogram chart. And what are 5 feet 7 inches? The chart measures total inches. So 5 feet is 5 times 12, 60 inches. Add the 7, that's 67 inches. So we go over here, look for 67 inches. And either place a dot there or imagine a dot. And then on this right-hand scale, we would go looking for 163 pounds. And put a dot there or imagine a dot. Connect the dots. And you should try this on your own, see what you get. And the middle scale is the body surface area. I got 1.91 square meters. So it was a little hard to get that because the scale is kind of tight there. But be careful you read those scales correctly. But I'm getting 1.91 square meters for this patient. So let's use that. Alright, so 1.91 square meters is the patient information. And the prescription is 30 milligrams per square meter. So there we've canceled the square meters off and we're down to milligrams of drug. And then 1 milliliter equals to 16 milligrams. So we want to cancel milligrams. I need milligrams in the denominator. So 16 milligrams down below, 1 milliliter up above. And that gives us milliliter units. So the unit calculations are done. We have milliliters, which is what we're supposed to get. And we end up with, let's see, 1.91 times 30 over 16 milliliters. And we could probably, we could reduce this fraction to 15 over 8. That means multiplying 15 times 1.91. I'd much rather multiply that by 30. So let's go ahead and do that. So 30 times 1.91, 3, 27, 2, 3, 5, and 2 decimal places is 57.30, or just simply 57.3. So this is 57.3 over 16. So let's divide 16 into that number. And how many decimal points do I want to go? Well, milliliters will probably measure as either a whole number or 1/10 of a 1/10 accuracy of a milliliter. In other words, 1 decimal place. So I'm going to go 2 decimal places here with this. Let's see, 16 goes into 57 4 times. It's 48. No, that's not right. 3 times. Sorry. Because 3 times 16 is 48. So I have a 3 here. 48. Subtract 93. Now I've got the decimal points lined up, so 16 now goes into 93. Let's see, it goes 5 times. That's 80, 13. And then 16 goes into 130 a lot of times, I think about 8 times. So 3.58. We're going to round it off to 1 decimal point. So that would be, in this case, 3.6 when it would round up. So this becomes 3.6 milliliters.